So today we are going to talk about evaluation of communication in parallel programs, particularly distributed memory parallel programs, right? So we'll start with a very simple model, right? It's called the Hockney model. Okay. So if you start looking at various models, so this is one of the earlier models that came out. After this, there have been lots of other models which have tried to give, better cost analysis of how costly it is to do communication, right? So this was one of the earliest models, but it's quite simple, right? So we'll start with this, and you'll find lots of models, log model, log GP model, and so on, right? Which are more prevalent today. But if you get the basics of the Hockney model, you should be able to read up and understand any of those models, okay? So we'll primarily focus on the Hockney model, right? So what does this model say? So it says that if, let's say, a node A is trying to send a message of size m, you can take m to be anything, we'll just take it to be words, right? Then what is the cost of this communication, of sending from A to B? The cost is Ts plus m times Tw, okay? So let's understand what is Ts and what is Tw. M is the message size, right? So that is clear. All right. Ts is basically the startup time, and Tw is related to bandwidth. Okay, we'll see how. So what is the startup time? So when A wants to send to B, right? So A has to basically do some processing. What is the processing it has to do? There's code involved. The code has to be executed on the processor, right? So that takes some time to execute. And then the message has to be copied into the network buffers, right? Any other buffering in between that has to happens. And in some cases, what the sender does is it actually first sends a message to the receiver that, I want to send you this data, right? Because this data may be huge, right? So it may send a message to B saying that, I want to send this huge data to you. So to avoid any buffering issues, are you ready to receive it? So B will not respond back until a corresponding receive is posted from some application, right? So when some application posts a receive corresponding to that send, it will reply back, yes, I'm ready to receive, right? And then A will send the actual data. So there is substantial amount of time that goes in this case in communicating with the destination before you actually start sending the data, right? Okay, what else is there? It takes some time for the data to go from one node to another node. If the nodes are connected by a direct link, it may not be much, but otherwise if if there are certain hops involved, then it has to be switched at various switches or at various nodes. So that involves certain cost. So typically we don't exactly calculate that. So we just kind of determine that for a network, right, for a given network, what is the average time it will take to go from one node to another node, right? So basically this is nothing but your latency. So the latency can be code latency or transmission latency, right? And anything else that may be involved over here, right? And similarly, when B receives the data, it has to again execute code, right? It has to make a receive call, MPI receive call, and there is a certain amount of code that is involved over there, right? So all of that is covered under startup latency, okay? So this is kind of like a constant cost, more or less, right? The part that is dependent on the data is determined by Tw. So what is Tw? Tw is the cost of transmitting one word onto the network, right? So how long does it take to transmit one word? Let's say your link bandwidth is 100 Mbps, right? Or megabytes, let's say byte, and let's say our word is 1 byte. How long would it take to transmit one word? So that will be nothing but 1 by 100, right? That is the time it will take to transmit one word. Here I'm assuming that 1 byte is 1 word, right? Okay. So how long will it take to transmit m words? M times 100, right? So this turns out to be your Tw, right? So is this clear? So this part is basically just saying how long it takes to send the message on the link, because the link has limited capacity, right? It has limited bandwidth. So based on that bandwidth, how long is it going to take to transmit it? And this term says all the other overheads, right? So there is one more overhead that we missed. So it's the execution of the code, it's the transmission on the links, and also transmission of the header, right? So typically whenever communication takes place, MPI appends a header onto the data, right? And then the lower layers may append something else, right? So all this additional header also has to be transmitted. So if the header size is h, then h times tw is an additional cost, right? But the header is always of the same size. So I don't need to account for this header over here. Since it's always constant h, I can just add this htw to the startup time. Okay, so it's a very simple model. There are certain other assumptions also over here. What are the other assumptions? So it assumes that you can only do one send and one receive simultaneously. So you cannot send to two different nodes at the same point in time, right? So in that sense, this is agnostic to the underlying topology, right? Given the topology, you could actually do something smarter, right? Yeah, this is one basic underlying assumption. It doesn't allow you to do more than one send at a time. It does not allow you to do more than one receive at a time, but you can do a send and a receive in parallel, right? You can do one send and one receive in parallel. Okay? And the other simplistic assumption over here is that it assumes that, no matter which node you communicate with, one thing is that your TS, the startup time, is the same, right? The other thing is that suppose A is trying to send to B and simultaneously C is trying to send to D, right? A is sending to B, C is sending to D. So it assumes that there is no contention, right? It assumes that the time that it will take will be TS plus MTW, because the paths of A to B and paths from C to D are disjoint. All right. In other words, one way to think about it is that you just assume that the underlying network is a clique, right? All the nodes are connected to each other. So in that case, what happens? There will always be a unique link from any node to any other node, right? So if A wants to send to B, it will use this particular link, and if C wants to send to D, it will use this link, right? So if you just assume that your underlying topology is a complete network or a clique, this model basically assumes that, right? That two messages from two different senders to different receivers, there is no contention, no congestion, okay? The other thing is we'll always assume duplex, right? So all the links are bidirectional. Okay, so if A is sending to B and B is sending to A simultaneously, that can happen in time TS plus MTW in the same amount of time, right? So both of them are allowed to do one send, one receive, right? So both of them are sending to each other, the same link is being used, but in opposite directions. That's fine.